Dr. RUFAIDA binti AZMI.
Hi, my name is NURSYAFIQAH AMIRA binti ISMAIL.
Hi, my name is AQILAH binti NORDIN.
Hi, and my name is IMAN binti TAWFEK.
Okay, so for chapter 2, we decided to choose to present about the laws of logic and quantifiers. Okay, now let's move to the topic, the laws of logic first. In this topic, we will learn about the logical equivalence, and I will present about the most common and famous logical equivalent that have in this topic. So, as we can see here, they are the most common and famous logical equivalent that we will learn in this topic. There are so many laws that we have to know, and after we considering this famous logical equivalent, we can apply these laws of logic in solving any kind of expression using the laws of logic. Let me show you some examples in solving the expression using the laws of logic. And now, let's move to the first question. Okay, for the first question, verify by using the laws of logic. The question is negation in bracket negation P and Q, and P in bracket P or Q equal to P. Okay, the first step we can do is write the question first. As we can see here, there's negation at this side. Automatically, we can apply the De Morgan's law. We can write like this. Okay, the next step, as we can see, there are two negation at here. If we see like this, we can apply the double negation law. The double negation law, it would become the original statement, that is P. So we can write P or negation Q in bracket and in bracket P or Q. The next step is, we can see there are two P at this side and this side. What laws that we can apply? We can use the distribution law. We can conclude this negation Q and Q in one bracket and let the P at the outside. What the next step? Okay, we can use the inverse law, that is negation Q and Q. It would be contradiction, and then as we know, if there are P or contradiction, we can write P using the identity law. So the final answer is E. Okay, for the second example, show that the following are tautologies by using the laws of logic. Okay, the question is P or Q and negation P implies Q. Okay, for the first step, we can change the implies by using definition of implication. We can write negation and change the implies to or we can call it disconjunction. Next, we can use the De Morgan's law, and then we can write like this. The next step, as we can see, there are two negation here. If there are two negation here like this, we can using the double negation law, and next, what will it be? So it will be original statement, that is P. Okay, the next step, okay, we can see that there are two disconjunction or O, that's this side and this side. We can apply the associative law, and then we can conclude that P or Q in one bracket like this. As we can see here, there are two statements same, but this one there that have negation, and this one there are no negation. So in this situation, we can apply the inverse law, and then this statement it would change to tautologies. Okay, for the third example, prove the following without using proof table. Okay, it means that we have using the laws of logic. Okay, so this is the equation. Okay, for the first step, we can use the associative law. As we can see here that there are conjunction and conjunction here, so we can conclude negation P and negation Q in one bracket and let R at the outside. Okay, and the next step, we can use the distributive law when we see that there are conjunction, disconjunction and conjunction here. So we can conclude Q or P in one bracket and let R at the outside. Okay, and the next step, we can apply the distributive law again when we see that there are conjunction, disconjunction and conjunction here. We can write R at the outside and let this bracket and this bracket in one bracket. And the next step, we can use the De Morgan's law, that we let the negation at this side at the outside, so it would become like this statement. The next step, we can see that there are P or Q here and Q or P here. We can use the commutative law to make this statement to become as the same like this statement. And now we can see that they are same, but at this side it have negation and this side there are no negation. So with this situation, we can apply the inverse law and it would become the tautologies. Okay, the next step, tautologies in R, we can use the identity law. The final answer, it would become R.
I will continue the presentation with the next topic, which is about quantifiers. In this part, we will learn about the definition of quantifiers, the different types of quantifiers, some examples, and do further exploration regarding this topic. For our first discussion, we will learn about the definition of quantifiers. In mathematics, quantifiers are defined as words that refer to quantities and they help determine how many elements in a statement are true. With that said, let's move on to the next discussion where we will learn about the different types of quantifiers. First, we will discuss about the universal quantifiers. The universal quantification of Px is the statement Px is true for all value of x in the universe of discourse or domain. The keyword for universal quantifiers is as highlighted, which is for all, and the notation for this universal quantifier, we can remember it as an upside down A. The notation itself is read as universal quantifier, but if denoted as below, we will read it as for all x Px or for every x Px. Now that we have learned about the definition of universal quantifiers and its notation, we will move on and do an example for universal quantifiers. Here we have the statement Qx where x plus 1 is less than x. And we have the domain that consists of set of integers. First, we can replace the x with values from the domain given. For example, first we replace x with negative 2. So the equation will be negative 2 plus 1 is less than negative 2. And for the second statement, we can replace x with 1. And we can write down the equation as 1 plus 1 is less than 1. Here we can see that both of them do not fulfill the statement as negative 2 plus 1 is not less than negative 2. Same goes for the second equation where 1 plus 1 is equals to 2 and 2 is not less than 1. In this case, we can conclude that the statement for all x Qx is false, and when the statement for all x Qx is false, it is called counterexample. Now we will move on to the next discussion where we will talk about existential quantifiers. The existential quantification of Px is the statement there exists an element x in the universe of distance or domain such that Px is true. The keyword for the existential quantifiers is as highlighted, which is there exists. And the notation for existential quantifiers looks like a reflected shape of the letter E. The notation itself is known as existential quantifier, but if we denote it as shown, there are several ways we can read it. For example, there is an x such as px, or there is at least one x such as px, or for some x px. Now that we have go through about existential quantifiers, we can do some examples. Here we have the statement px where x is equals to x squared and the domain given is set of integers. We are asked to find the truth value of the statement px where x equals to x squared. Unlike the universal quantifiers, statements of existential quantifiers can be true even if there is only one value that fulfills the statement and the rest are false. So we can write simply x is equals to 1 plus 1 equals to 1 square. And here we can see 1 square is also equals to 1. From this statement alone, we can conclude that in this case, the statement there exists x px is true. Now that we have discussed the main types of quantifiers, we will now talk about another type of quantifiers called the nested quantifiers. Nested quantifiers are quantifiers that occur within the scope of other quantifiers, which means that there is more than one quantifier in a single statement. In the slide, we can see the example. Here we can see for all x, there exists y, q, x, y. From this statement, the existential quantifier occurs within the scope of the universal quantifier. This is what we refer to as nested quantifier. Now that we have defined what is nested quantifier, we will move on with an example. Here we have the statement that for all real numbers x and y, where x plus y is equals to y plus x, and let us assume that the domain given consists of all real numbers. We will denote this as for all x and y, x plus y is equals to y plus x. Then to find the truth value of this statement, we can try replacing the x and y with real numbers. For example, we can put x is equals to 2 and y is equals to 3. Then we can rewrite the statement and solve the equation and determine whether the statement is true or false. We can see that on both sides, the total of x and y are the same. So we can conclude that the truth value for the statement for all x and y, x plus y equals to y plus x is true. Now that we have seen the different types of quantifiers, let's see another example where quantifiers can be applied to. Besides combining two quantifiers to form a nested quantifier, we can also use quantifiers to translate word statements into logical expressions. Here is an example. Let's try translating the statement, the sum of two positive integers is always positive, into an equivalent logical expression. First of all, we must understand what the statement is saying. From the statement, we can understand that it is saying that for every two integers, if both integers are positives, then their total is also positive. So from the statements, we can see that two integers are involved. In this case, we can replace the two integers with x and y. X and y will be represented as the two variables used to make the word statements. We can then arrange the equivalent logical expression using quantifiers and the statement that we understand. Thus, we will get for all x and y, if x is more than 0 and y is more than 0, then x plus y is more than 0. The reason why we use more than 0 is because from the statement it is said two positive integers. The value after 0 will always be positive, and that is why we use this symbol and its value. That is all for my part of this presentation. Thank you.
The topic under Chapter 3 is Proving Techniques. We will give a brief introduction and show a few methods that can be used to solve the question. We will also give an example for each method by giving an explanation that can make you understand it better. The mathematical proof is said to be a convincing argument expressed in the language of mathematics. 7 methods that can be used to prove mathematical statements are forward-backward method, construction method, choose method, specialization method, contradiction method, contrapositive method, and induction method. All these methods are used to determine whether the mathematical statements or expression is either true or false. When proving mathematical statements, there is a condition before choosing which method needs to be used. If the statements are in a conditional statement, we can use all those methods except for the induction method to do the proving. 2 methods that we decided to show are forward-backward method and construction method. Before moving on to the first proving method, there are a few definitions that we need to know before doing the proving. Firstly, n divides m. This can be written as m is equal to k times n for some integer k. Secondly, if it is said that it is an even number, we can write them as n equal to 2k for some integer k, while for odd numbers, we can write them as n equal to 2k plus 1 for some integer k. Next, for rational number, r can be expressed as the ratio of the 2 integers p and q where denominators q does not equal to 0. The first method is the forward-backward method, which is the most basic one. This method is used to prove the conditional statement if A then B. Assuming A is true, then use this to show that B is true. The forward-backward method involves 2 processes, which is the backward process to reach the conclusion B is true, while the forward process to make specific use of A. Hence, it is called the forward-backward method. To start backwards, ask a key question about the conclusion you are trying to prove. There are many ways to ask this question, depending on the content, and some key questions may be completely unhelpful. But critically, the key question is abstract and is of the form, how can I conclude that the statement is true? The forward process involves deriving from the statement A, which you assume is true, to some other statement, A1 to A2 and so on, that you know is true as a result of A being true. Lastly, they are directed toward linking up with the last statement obtained in the backward process. I will show you some examples on how to use the forward-backward method to prove a conditional statement. Question number 1. Prove the proposition if n is a positive odd integer, then n times n plus 2 is an odd positive integer. There are 2 types of proof. The first one is the analysis of proof. First of all, we need to identify the hypothesis A and conclusion B. Secondly, we need to see the conclusion B and apply the abstract answer that contains symbols and notation to give a specific answer. By doing that, you will obtain a new statement which is B1. Next, derive from A to become A1 that you know to be true and continue with A2 and so on. This process will repeat until the statement can link with the last statement from the backward process, which is B1. We can see here that A3 is linked to B1. Thus, this proves that the statement is true. Another type of proof is condensed proof. Condensed proof is the elaboration of the analysis of proof done just now. The condensed proof of the question just now can be written as n is a positive odd integer can be written as 2a plus 1. N times n plus 2 equal to 2a plus 1 times 2a plus 1 plus 2 implies n times n plus 2 equal to 2a plus 1 times 2a plus 3 and expand the expression. Factorize n times n plus 2 equals to 2 times 2a squared plus 4a plus 1 plus 1, and we let p equals to 2a squared plus 4a plus 1. Thus, n times n plus 2 equal to 2p plus 1 for all integer p is an odd positive integer. Moving on to the next question. Prove that if the right triangle XYZ with sides of length x and y and hypotenuse of length z has an area of z squared over 4, then the triangle XYZ is isosceles. Just like the previous question, we are going to identify the hypothesis and conclusion A and B. Apply the backward process to create a new statement B1, which is x equal to y. For the first forward process, we can apply Pythagorean theorem to derive A1. For A2, we can use the formula of a triangle, which is B times H divided by 2, and then insert the value into the equation to create A3 and A4. We can factorize the equation in A5 to A6, which is x equals y. We can see that A6 is same as B1, so it is proven. For condensed proof, it can be written like this.
Hi, my name is AQILAH binti NORDIN. I would like to continue this presentation with the title from chapter 3, which is the construction method. Previously, you have been heard the explanation for forward-backward method. This method is the other option from the conditional statement to be considered. This method had been used when the conclusion that involved has an accentuation quantifier, or can be easy to understand that in conclusion, it will have an object that did not have in hypothesis. It just appeared in conclusion. It had different object or can be called variable. The accentuation quantifier notation is there is, they are, they exist, or it was also can be notation such that, for which. All of this is the accentuation quantifier. This method will be used when the conclusion, which is P, is in the form of there is an object with a certain property that such that something happened. A implies P, that in B it has accentuation quantifier. To solve by using this method, it has a step that can be followed, so it will be easier for us to solve it. Okay, for this first step is we need to identify the object, certain property, something happened that can be detected in the question. We need to choose it carefully when reading the question. Next, the second step is we need to construct the object. We can use the hypothesis to guess which one is it. So it will make us devise an algorithm for the procedure. Lastly, we can show that the object has a certain property and we specify that something happened. So maybe for the easier word is first find the hypothesis and conclusion. Then the step that we can use is by the conclusion, which is P, we will use it to find the object, and when we get it, so we can insert it to check if it equivalent or not with the hypothesis, and finally we will define if it was a true or false. There are a few examples that I will explain. First of all, example 1. If P and Q are even integer, then 3P squared plus PQ is divisible by 2. Actually, it has two types of answer that can be considered as proof. It is an analysis of proof and condensed proof. Basically, the condensed proof will be written after the analysis of proof answer. It is because this type will list down the step that had been used to answer the analysis of proof. It is more like an explanation in words. Okay, for the analysis of proof, in this question, we'll be start with which one is A and B. So from the question, we can list that A is P and Q is even integer, and the B is 3P squared plus PQ is divisible by 2. From that, we can list the B1. In the definition of divisible, we can write it as 3P squared plus PQ equal to 2K. You may rewind this video to refer the definition that I have been listed in the introduction of this topic. K that I have been used is not fixed. We can change it based on our preference. With the appearance of K, so it has now certified why this method is used. Since P and Q are even, then we can use the definition of even number P equal to 2A and Q equal to 2B for A1. The object that P added must be different. Next, we can continue it with A2. So from A1, we can insert it in B1 B1 to be solved. It will become like this, and the end of this we need to try to make it similar to B1. So we need to factor the equation. Then we need to let it with something, such as in this question I have been let it with M. So after that I can use it to make an A3. And finally this question has been equivalent. The A3 and B1 are similar to each other. Next, example 2. Prove that if A and B are real number with B not equal to 0, then the two circle x squared plus y squared equal to A and x minus B bracket 2 plus y squared equal to C intersect. First of all, we can list down the A and B in this question. Then we can use the B to make B1, which is x and y that did not have in A, so it must be used this method. Because of that, we need to construct x and y. We can use the two equations in B1 to get it. Then it will be like this. After having simplified, insert 1 into 2, we will get the x. Then we continue it, we insert the first equation, and finally we get the y. After that, we can list the x and y for A1. Then we can continue it to insert the x and y in the equation. For A2, we can calculate it by using the first equation and A3 with the next equation. Then finally we can conclude is that A4 and B1 are equivalent. That's all from me. Thank you.
In conclusion, from this assignment, we have learned that math is more than just numbers and calculations. It helps us sharpen our minds and expand our imagination in order to understand a statement or a situation thoroughly. The methods we have learned may be complicated at first, but with practice we were able to do better with our calculations and understand more the logic behind math. By understanding the methods well, we could also simplify a lengthy statement into statement that uses logical connectives, variables, and so on. In all, we may find math to be complicated, but math actually helps us to understand a complicated situation or a statement in a more simpler way.